Okay, let's get started. Bismillah ar-Rahman ar-Rahim, wa salatu wa salamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. In this lecture, we are going to present the basics of a neural network. So, in the previous lecture, we have already introduced logistic regression with one simple neuron, and we have explained the process of the forward propagation and also the backward propagation. So, just to make a summary, we have assumed that we have an image as an input. For example, we have two pixels, x1, x2. They will go through the neuron. First of all, we are going to make a linear transformation, z equal wx plus b. And then you will add a nonlinear transformation by applying the sigmoid function. Okay, and here, finally, we will calculate the loss. Okay, and the loss we can calculate it using different ways. For example, it can be the absolute loss or the quadratic loss, or also the cross entropy. So in our computation, we have considered to use the cross entropy, and we wanted to optimize the loss with respect to W and B, and for this we had to calculate the loss with respect to A first, so we come up with this expression, and then we calculate the loss, the derivative of the loss with respect to Z, and at the end we were able to calculate the derivative of the loss with respect to W1, W2 and B, and we got the following expressions. And after we get the derivatives of the different of the loss function with respect to W and B, we will update the weight and the bias according to the following equation here. So W1 is equal to W1 minus alpha dW1, same thing for W2 and same thing for B, and alpha is the learning rate, And I think during the programming assignment, you had the time to apply all these different equations, and now I think you have a good understanding about how to perform the forward propagation and the backward propagation. So the objective of today's lecture is actually to generalize this to multiple or to deeper network with multiple nodes and multiple layers. Okay, so at the end of the lecture, we are going to reach the following equations, which are the generalization of the equations that we have obtained for the logistic regression with only one neuron. Again, in today's lecture, we are going to consider logistic regression, but in this case, we will consider that we have multiple layers. So we have the input layer, we have the hidden layer. The first layer is called the hidden layer, and you have one output layer. And here, using multiple layers and multiple nodes, it has more advantage as compared to using only one node, because you will have every node is going to calculate a particular information. So this helps to better extract the features from images or from the input data and convert it to the output, especially if we have a lot of data. If we have a lot of data, usually our network has to be bigger. Otherwise, if you use very small networks, we are not able to learn all the different features of the input data that we have in hand. And basically, okay, we cannot increase indefinitely the number of nodes and the number of layers because at some point in time, we may degrade the performance. So again, the number of nodes and the number of hidden layer is also a hyperparameter that try to be adapted according to the data, to the scale, to the size, and multiple other things. Yes? Yes, sure. Yes. Okay, so at the end of this lecture, we will be able to derive the forward propagation and the backward propagation for a neural network with 3 layers, as you see here. And you will see that this will be just a generalization of what we have seen in the previous lecture with only one neuron. So the learning outcome of this lecture are the following. First, you will be able to understand the hidden units and hidden layers. You will be able to apply a variety of activation functions in a neural network. You will be also able to build your first forward and backward propagation with a hidden layer, and you will be able to apply random initialization to your neural network. You will become fluent with deep learning notations and neural network representations. And finally, you will build and train a neural network with one hidden layer. Okay, so this was our starting point. We have here an image, let's say with 3 pixels, and we have one neuron with W and B. And finally, we will calculate the estimate y hat, which is equal to A sigmoid of Z. So these are the equations that captures the neurons. As you already introduced, you have a linear transformation to calculate the Z, then nonlinear transformation to calculate the sigmoid of Z, and finally we calculate the loss, and then we calculate the derivative in the backward direction, the backward propagation, and this will allow us to calculate the derivative to calculate the new weights. Now let's consider a more general representation with 2 layers. Okay, one hidden layer and one output layer, and of course we have the input layer, that is the input image itself. So in this particular example, we have the first layer, so we give it an index of 1, and you have 3 neurons. So, and we have a second layer that we give the index 2. Okay, and finally we will calculate also the same output using logistic regression, whether the image contains a cut or not cut. So we calculate in the same way y hat, and will be equal to the sigmoid of Z, and Z will be calculated this time from multiple nodes instead of being calculated of one node. Okay, so in the same way, we will have a first layer that will calculate Z1, which will be a weight matrix W1 multiplied by the input image X plus B, and then we will apply the sigmoid to Z1, and then we will have the output for the second layer. So in the second layer, the output of the layer 1 will be considered as the input of layer 2. Okay, so we can see the output of the hidden layer will be provided as input to layer 2. This is why here we are going to have a weight matrix W2 multiplied by A, and A here is actually the output of the first layer. And we will add the bias for the second layer, and finally, after calculating this linear transformation, we will calculate the nonlinear transformation by again applying the sigmoid function. And at the end, we will have the loss. So the loss here will be calculated with respect to the ground truth and the output of the second layer. Okay, so here we will have multiple nodes, and every node is going to provide the computation for the next layer. So this is the overall structure. Yes. W2. Yeah, every layer, actually, this node has W and B, this node has W and B, this node has W and B, and this node has W and B. Okay, so W2, B2 are the weights of the second layer. So we will see in details how we construct these matrices. Okay? Yes. Yes, of course. When we calculate the loss, we are going to do the derivative of the loss with respect to the weights of the second layer and also the weights of the first layer. Okay? And then we will calculate the new weights in the second layer and also in the first layer. So we will go in the backward direction. But here we have 2 stages instead of only 1. Okay, so you have to calculate the derivative of the loss with respect to this output, and then to this transformation, and then to this W, and then to this output here, and so on, until you get back to the first layer, initial layer, that is layer 1. Okay? Yes. Yes. In the previous assignment and the previous lecture, we only considered one node. In this lecture, we are going to make a generalization by having a hidden layer with multiple nodes and an output layer with only one node. No, it's A. Look, this one is going to calculate an A, this one is going to calculate an A, and this one is going to calculate an A. So we will have a vector of 3 A values, and this vector will be the input for the layer 2. So the vector of A1, A2, A3 will be like x1, x2, x3, but applied to the second layer. Okay? Yes. So this A is going to be like the pixels in the second layer. Exactly, yes. Yes. Yes, of course. Now, if we have complex data and we have a lot of data, we cannot rely on very simple neuron. Okay, it will not be able to capture all the different features that are in the image or in the input data. This is why we need to increase the number of hidden layers, and we need to increase the number of nodes in each layer. So as already mentioned, the number of hidden nodes in each layer and the number of layers is hyperparameters. You can try different configuration and check which one is going to give you the best result. And this depends from a lot of other factors. Of course, yes. Yeah, now designing the appropriate architecture is a challenging problem. And this is why in the literature there are several people who designed architectures that are currently used by others. But you can also design your own architecture, and usually you have to do a lot of trials in order to find the best result. And people now always try to create a new type of architecture for classification, for object detection, and they do the benchmark on big image data set, like for example the ImageNet or the COCO data set, okay, as a benchmark. So these data sets are used in order to compare the accuracy of different type of architectures. Is it clear? Okay, so now let's go a little bit more concrete and try to explain the neural network representation. So we have here the input layer, which is the image X, and we call it A0. So A0 is equal to X because this is the input, okay? And it has the 3 pixels here. And you have a hidden layer. Every layer has an activation function. So what is the activation function? It's the sigmoid function applied to the linear transformation Wx plus b. Okay, and this is going to give the A1, okay, A11. So this is the first output in the first layer. A21 is the second output in the first layer. And A31 is the third output in the first layer. And A41 is the fourth output in the first layer. Okay, so the hidden layer will have here, in this particular example, 4 outputs. Okay, so these outputs will represent the input for the layer 2, which is the output layer in our case. We can have additional layers in between, but in this lecture we are going to consider only these 2 layers, hidden layer and output layer. In the next lecture, inshallah, next week, we are going to generalize this to multiple layers with, for example, 3 hidden layers or 4 hidden layers or 5 hidden layers and more. But today we will try to understand what will be the equation, the forward propagation equation for this simple network. This network is still simple. It's a little bit deeper than, for example, only one neuron. But of course, we can have a larger number of hidden layers in the middle. Okay, and at the end, so the output of the hidden layer will be considered as the input for the output layer. We will have one activation function, A12. So this is the first activation in the second layer. When it takes this input, okay, which is the output of the first layer, it will always calculate a linear transformation Wx plus b, and then it will apply the sigmoid, and this will represent the y hat. And the y hat is also notated as, we can denote it as A2, okay, A2. So you can see here A1 is the whole output of the hidden layer, and A2 is the whole output of the output layer or the second layer. And finally here, the value should be either 0 or 1. But of course, if the value is different from 0 or 1, it means that we have a loss that is greater than 0. And in this case, we have to calculate in the same way the backward propagation and the derivatives. Okay, so what is A1? A1 basically is a vector that is composed of A11, A21, A31, A41. We can consider all of these as, this is a matrix. Okay, a matrix because this one is a vector, this one is a vector, and this one is a vector, and this one is a vector. We will see in more detail what is the shape of all these vectors in the next slides. Is it clear? Can you repeat? It's clear here. Look, هذا الرقم هذا اللي ما بين between brackets, this is the layer number, and the one in the bottom is the node number. Yes. Any other question? Okay, in any case, now we are going to go for, okay, I just added him, but now we are going to go for Salat, for Asr, and we will come back later, inshallah. But is there any other question before we go? We may have like a few minutes to respond to your question. Yes. Yes, this one is going to produce a vector. Okay, because here we have a vector as input. Okay, so it will have a weight matrix that is a matrix multiplied by this vector multiplied by the bias. Okay, we will see now after that in the next slide that we will see what are the different shapes of these outputs. But for now, just understand the relation between them. Okay, and most importantly, understand the notation. Is there anything difficult with the notation? Is it clear? Yes. Yeah, the benefit of hidden layer is to extract more features. Look, this node is going to extract features, this node is going to extract features. So what is features? It's the W and B, صح ولا لا? Okay, if you have multiple W's and B's, you will have multiple features to calculate. So, yeah, from one image, yes. X1, X2, X3 are the pixels. Here we consider only one image in the input. We will later generalize to multiple images. Okay, and we use hidden layer or multiple hidden layers in order to increase the number of features that we can extract. And of course, this is beneficial when we have complex data that contains a lot of features. Okay, Bismillah ar-Rahman ar-Rahim, wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Let's continue our lecture. So here we have introduced the general representation of neural network with one hidden layer and one output layer. Let's focus more on the output of the neuron. Okay, here we have 4 neurons in the first layer and 1 neuron in the second layer, and all these neurons will do the same thing. Okay, so for example, if we consider any of the neurons into the first layer or the hidden layer here, so you can see that they are all connected to the input x1, x2, x3. So every node or every neuron here is going to calculate the linear transformation wx plus b, which is z, and then it will apply the sigmoid function to calculate the output a. Okay, so I will have an output a here, 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 and here, and finally it will calculate here the output for the neuron according to the equation that you have already introduced and everybody knows. Okay, so this is only one neuron, inside only one neuron, so this will happen in the first neuron, okay, which is the, it will provide an output with, okay, so ALI is the output in layer L in the node I. And you already explained here, so this is the first output in the first layer, and then this node is going to calculate Z1 of 1, okay, so it's the output Z in the first node of the first layer equal to W1. So the weight matrix here is going to be related to the node and to the layer. So every node will have its weight matrix. So that's why we have W1, 1 multiplied by X, which is the input vector, plus B1, 1. So this is the bias at this node. So this node will have W1, 1 and B1, 1. These are the parameters of this node. And of course, later we will calculate the sigmoid of Z1, which will provide the output A1, 1. So this is the output in the first node of the first layer. So if we want to calculate for the second layer, for the second node in the first layer, the same thing. What only changes here is just the index of the node. So here we will calculate Z2 of 1. Z of the second node in layer 1 is equal to W2, which is the W of this node in the layer 1, multiplied by X, because it is related to all X1, X2, X3 values, plus B21. And again, we will calculate A21, which is the sigmoid of Z21. And we will do the same for all the nodes. Okay, from A11 to A41. And this is going to give the equation. So this is the equation of the first node. These are the outputs of the second node. These are the outputs of the third node. And here it's the output of the fourth node. And all of them, they are calculated in the same way. Okay, so everyone will learn its own W and B. And here it will learn its own W and B. Every node has weight and also bias. So we will have 4 outputs from A11 to A41, which is the outputs here. And these outputs will be the input for the next layer. So these are the elementary equations, but we can use vectorization. And I think you have already used vectorization in the Python assignment, which is to put everything in a matrix. So instead of calculating them individually as we did here, we can calculate them here as a matrix. So we can consider the matrix Z1, which will be the output of all the nodes here. Okay, so Z1 will be just the matrix that contains Z11 until Z41. We will stack all them together. Okay, and here this matrix will have the weights W11. So this is the first weight, second weight, and third weight of this node. Because every node will have 3 weights, because here we have 3 pixels. And same thing we will have for W1, for W31, W21, and W41. We will have 3 values, because here we will multiply by X1, X2, X3, and we don't forget the bias. Okay, so the bias here we have 4 values, because every value in one node, B11, B21, B31, and B41. So this expression here is equivalent to all these equations. Okay, instead of writing them here individually, we will write them down as a matrix representation. And now if we multiply this matrix by this vector here, we can have W1x plus B, W21x plus B21, and so on. And to which we add the bias vector. Okay. Is it clear so far?
Yes, doctor, but I have a question.
Yes.
When we say input vector, that's mean, doctor, array of 1 column, right?
Yeah, now we are talking in the case of one image. So this is the input vector. It's the pixels. This is the first pixel, the second pixel, the third pixel, and so on.
Okay, and is each pixel in 1 row and all of them in 1 column.
Yeah. Okay, so here, this is why, look, we have 3 pixels. So every W Li has 3 values. Okay, so this value will be multiplied by this pixel, this value will be multiplied by this pixel, and this value will be multiplied by this pixel. Okay.
Doctor, I have a question.
Yes.
Each node has its own W and B, or did I understand it wrong?
Yes, each node.
So each node has its own W and B value?
Yes, so this node, for example, it has W11 and B11. And W11 is composed of 3 values. Okay? Because here, why?
Yeah, I get it.
Everyone is going to be multiplied by pixels. If I have 100 pixels, so W11 will have 100 value in 1 row. Okay?
Yes, thank you.
Okay. Okay, so now we will have Z1 equal to this expression. Okay, so W1 will be just W1 multiplied by X is this one, is this expression plus B. Okay, so all this matrix here is called W1. Okay, so we can write Z1 equal to W1 X plus B1. And B1 is contains the 4 values of this first layer. And then if we want to calculate A1 for the whole layer, for the whole hidden layer, we just need to apply sigmoid to Z1, and then it will be the sigmoid of Z11, the sigmoid of Z12, and then it will calculate A11, A21, A31, and A41. And in the assignment you have already known that sigmoid can be used for vectorization. It will be just applied to the individual values of Z, even here, over here. Okay, so let's make a summary. Now, given a neural network with one hidden layer and one output layer, we calculate the different output values, A, I, L, in each layer L, okay? And then, for example, for the first layer, we have Z1 equal to W1, A0 plus B1, and then we can calculate A1 equal to the sigmoid of Z1. And here Z is actually the matrix that contains all the input values over here. So same thing. Now, considering this neuron, it will have an output as A1. So it will be multiplied by W2 plus B2. So basically, we will have the same equation for every layer. What changed is only the index. Okay? Only the index will change, and we will have exactly the same type of equations. Okay. So let's look now at the dimension of vectors, which is really very important. Now, if we look at A0, here we have 3 pixels. So the dimension of A0 will be 3, 1. We have 3 rows and 1 column, right? And now this is 3, 1, 1. This is the shape of A0. So this makes now for W1, it will have a shape of 4, 3. Why 4? Because here we have 4 outputs. 1, 2, 3, 4. So in every node I have a W, and for every pixel I will have a W. So the shape of W1 will be 4, 3. And this will help, this will allow to make the dot product between W1 and A0. And what is the shape of B1 now? What is the shape of B1?
It's the number of nodes, doctor.
It's the number of nodes. It's 4, 1. Okay? 4, 1. And this makes... And yeah, just one moment. And this makes good sense, because now if we make the dot product, we have 4, 3 and 3, 1. So the resulting of the dot product will be 4, 1. So we will have a vector of 4, 1 plus a vector of 4, 1, which will be the shape of Z1. It's 4, 1. Yes, Abd Moaz.
Yes, Talal. Didn't we learn in the assignment that B is scalar? So why is it vector here?
Yes,
because we initialize B. I remember prime it as
because
0.
In the assignment you have only 1 neuron. Okay, and here you have 4 neurons.
So B is dependent on the number of
neurons. So now, for example, if we look at A2, we will have a scalar. If we look at A2, like, look now, let me finish the whole example. Now, if we look at A1, of course, A1 and Z1 will have the same, shape, because sigmoid will not change the shape. Okay, it will have the same shape as Z1. So A1 will have the same shape as Z1. A1 will be the input of the second layer of the output layer. So it will have a shape 4, 1. And how many outputs we have in the output layer? How many?
Output layer 1.
We have 1 output. What will be the shape of W2?
4, 1, 4.
Okay, so we have only 1 output here. So the shape of W2 will be 1, 4. Okay, because we have only 1 output. And 4 because here we have 4 values in A1. And if you multiply, if you make a dot product of 1, 4 by 4, 1, it will result in 1, 1, which is also the shape of B2. And B2 here is a scalar. And this makes sense, because at the end we are going to have 1 value which is between 0 and 1. صح ولا لا?
Yeah, the prediction.
Yes.
Yeah, the prediction. So, and then A2 will be 1, 1, the same shape as Z2. Okay, so now you can understand the shape, the relation between the shapes, between the input, between the weight matrix and the bias. Any question here?
Yes, doctor, please. Could we say now, doctor, we have two nodes in last layer, A2. What will be W?
If you have two nodes, it means you will have two outputs.
Okay.
Okay.
So
W will be 2, 4.
Okay. So always, doctor, last layer should be or must be one node to make it one output?
No, this is in the case of logistic regression, because in logistic regression we have a sigmoid function at the end that will give one value between 0 and 1, a probability. But for example, if you remember the case of cut and not cut classifier, and then we will have more other cases, we have multiple classes in the output. Okay, so in this case we will have outputs that contains multiple neurons. So the output layer will contain as many neurons as the number of classes that you have in your network.
Okay. The output layer.
So
yeah, so this is a very particular example related to logistic regression, which outputs a value between 0 and 1.
So if we have multiple classes, so like if our model has like I don't know, 3 classes, we're gonna have 3 neurons in the output. Right?
Yes. So we will make later on, maybe in the next lecture, we will check the case where we have multiple nodes in the hidden layers and multiple nodes even in the output layer. So we are just introducing this notation slowly, okay, in a progressive manner. But we are going to go for more generalization later on. So does this make sense for everyone?
Yes.
Okay. Okay, now let's look at the case of vectorizing among multiple training examples. So far we have talked about one training example. We have only one image which contains 3 pixels, x1, x2, x3. Okay, so for every x, we are going to calculate one prediction, A2 or y hat. Now imagine that you have an M training examples. You have several images. So for every image, you will do the same thing. So for the first image, you will calculate A2 for the first image. So here, look at the notation. So between brackets, it's the number of layer, and between parentheses, this is the index of the image. Okay, and here y hat. Now for the second image, you are going to calculate for x2, you will calculate A2, 2. So A for the second layer and the second image, it will have its own estimate. And if you have M training examples, you will calculate xm, A2m equal y hat of the M training example. Okay, so for the indexing, as already mentioned, the layer is represented between brackets, and the index of the image is represented between parentheses, so do not confuse that. So for all images from x1 to xm, what we can do, we can make a for loop like this. So for every image, we can calculate z1 of I, and then calculate a1 of I. So this will be the output of the ith image in the hidden node, in the hidden layer, and then we will do the same for the output layer. Is this understood?
Clear. Yes.
Okay. But using a for loop is not the best approach, because from computation perspective, it will be much slower, especially if you have a large data set and you have a huge number of computation to perform. And again, the best way to do that is to use vectorization. It means we try to make a vector representation of this for loop. So how to do that? So this is now using the for using the for loop, the equations that we have developed, and now we will look into how we can vectorize this, how we can vectorize multiple training examples. Okay, so in this case we are going to consider X as the matrix that contains all the images. So we will process the images into batches. Okay, we will process the images into batches. Instead of processing image by image, we're going, for example, let's consider 100 image or 64 images, putting them into one matrix, and we process them as a batch. So why we do that? Because this is more computationally efficient. This is more computationally efficient. Okay, so considering M training examples, okay, we can use vectorization. So we can calculate Z1 as W1 multiplied by X plus B. So the T here is just for the matter of matching the dimension between W and X. And then A1 will be the sigmoid of Z1. And then Z2 will be W2 A1 plus B and A2 Z of sigmoid of Z2. So the only difference here, instead of making Xi, we're going to do just the whole X matrix. All of this. We will do the whole computation at once using vectorization. So this notation here is equivalent to this for loop, but this one is more computationally efficient. And this is why we use vectorization. And even in the assignment, you have already used the vectorization approach. Okay. Okay, so with this, we come to the expression of forward propagation among multiple training examples. Now let's talk about activation functions. And what is the role of activation functions? Is to add nonlinearity to the model. Okay, because if we don't use activation functions, basically the model will be just a linear regression, and we don't want to have that. Okay, and we said in the previous lecture that the nonlinearity, it allows to learn more complex patterns and more complex features from the input data. Now, what kind of activation functions we can use? There are multiple types of activation functions. So far, we have only talked about the sigmoid. Okay, so this is in the green curve, it's the sigmoid function that you already know, which has values between 0 and 1, okay, and has an S curve. There is another function that is also commonly used in deep learning, which is called the tan-H. Okay, and the tan-H, it has values between -1 and 1. Okay, it has similar shape to the sigmoid, but its values are between -1 and 1. And it adds nonlinearity also. So the activation function is also a hyperparameter. We can tell that, for example, sigmoid is better than tan-H or from others. But basically now, for example, if you look at the most common classification projects, most of the people, they are using the ReLU activation function that I will introduce in a while. But nothing also prevents to change the activation function to tan-H or sigmoid to try to learn different type of patterns. Now, okay, if you apply the activation function, instead of making the sigmoid of Z1, you can just make tan-H of Z1, and this will also add nonlinearity. And you can see the difference in the expression of the sigmoid function and the tan-H function. So the tan-H function can be expressed as the exponential of Z minus exponential of minus Z divided by exponential of Z plus exponential of minus Z, or can also be written in the second expression here, exponential 2Z minus 1 divided by exponential 2Z plus 1. And as you already know, this is the expression of the sigmoid function. It can be used here. So just here to summarize that, when it comes to using the activation function here in the hidden layer, you can try different types of activation functions. But of course here in the output layer here, the sigmoid is more appropriate because the output that we have in this particular case is a value between 0 and 1. So if we use tan-H here in the output, you're not going to find the value between 0 and 1. You're going to find value between -1 and 1, and maybe not. This is not appropriate for the logistic regression. So for the logistic regression, we use the sigmoid in the output layer. But in the hidden layer, you can use other types of activation functions. So let me give you a walkthrough on different activation functions. This is the sigmoid and its expression and shape. There is a very popular activation function that is called the ReLU activation function. And we have already used it in the cut not cut classifier. Okay, and it's very simple activation. So if x is negative, is going to be rounded to 0. And if x is positive, it will be just equal to x. So here you will have y equal to x. This is the ReLU activation function. You have the tanh activation function, and it has values between -1 and 1. And you have already introduced its expression. And you have also leaky ReLU. So the difference between ReLU and leaky ReLU is that the second one, leaky ReLU, it has a value that is 0.1x for x negative. And here you have x. So here this will allow to learn more patterns for negative values of x. Okay, so the leaky ReLU can sometimes lead to learning some additional patterns as compared to the ReLU function. But so far in most of the classification problems that I have seen, at least the common one with the state of the art, they use the ReLU activation function. There is also the max out, which is equal to the max of W1TX plus B1 and WTX plus B2. And you have the ELU activation function, which is equal to x if x is positive and is equal to exponential x minus 1 multiplied by alpha if x is negative. So all of this, the common property among all these activation functions is that all of them, they will add nonlinearity. Okay, all of them, they will add nonlinearity to the neural network, and this will allow to learn advanced patterns and features from the input data. Okay, so one possible way is, for example, we can use the tanh in the hidden layer. So if we use tanh activation in the hidden layer, we will have, for example, here z1 equal to w1x plus b, and then a1 will be equal to tanh of z1, because here we have used the tanh activation function. And z2 will be equal to w2 a1 plus b, and a2 equal to sigmoid of z2, because here we use the sigmoid as already explained, because we need a value that is between 0 and 1. Okay, so this is just to say that you can try different type of activation functions and check which one could lead to better result for learning the patterns from the input data.
Doctor?
Yes.
Yeah, how does it help when an activation function go to the negative side? Like you said, by learning more patterns. How do we learn more patterns by having negative values?
Yeah, this is a good question, basically. So basically the positive value, it means that we have more intensity in the image. And this is like the feature that we would like to capture. We would like to capture the pixels that has more intensity than the others. But it turns out that in some cases, like instead of zeroing all the negative values, we can just provide some tolerance to those, to some negative values. Okay, so instead of discarding them totally, okay, we can add them, because now when you have an image that is completely dark, does it, even with human eye, can you distinguish anything?
No.
It's difficult. So it's kind of like this. But for example, if the darkness is a little bit, not too much, you can still learn something. Okay, so instead of discarding these low intensity pixels, you can add them into your model. So maybe they can bring some additional value in the learning process. Okay.
Yeah, understood now.
Is there any other question? Okay. Okay, in the same way, we can also use the ReLU activation function. Okay, and this here, the impact will be that the output of the first layer will be equal to the ReLU of Z1. And then, of course, all the other things will remain the same. And of course, here you will see that the activation function is going to impact all the other layers that comes afterwards, because the value of A1 with ReLU will be different from the value of A1 with sigmoid or the value of A1 with tan H. So every activation function will help you to learn in a different manner. And you can try different ways and check which one will provide you the better learning performance.
Doctor,
Yes.
since ReLU gave me also between 0 and 1, why we did not use it in output layer?
So ReLU doesn't give you between 0 and 1, because here you have the equation y equal to x, and y and x can go much bigger than 1. Look for x equal to 3, y equal to 3. It's not 1.
Okay,
Okay?
clear.
Yeah. Okay, so why we use activation function? We have already talked about this a couple of times. Okay, because simply, if we use a neural network with everything linear, with linear activation function, at the end you will end up by A2 just equal Wx plus B, okay, which is just a linear regression. So in this case, the whole neural network will simply become a linear regression, and this is not going to perfectly match the input data, especially when the data is very complex. So you can follow the equation here. If you calculate Z1 equal to W1x plus B1, and let's say A1 equal to Z1, we just have linear transformation, so here almost an equality. And if you apply here Z2, so A1 will be Wx plus B1 plus B2 here. At the end, you will end up by making an expression of A2, just linear transformation of x, which is the input. So we will not learn anything here. We cannot learn something more than a linear regression model. And linear regression, it's good for some kind of data, but it's not good for all type of data. There is data that doesn't have linear relationship pattern. So we need to find more complex patterns. And it's only with the activation functions that we are able to learn these complex patterns. Okay, more complex equations rather than just a linear transformation of the input to find the output. Okay, so why the activation function in neural network without an activation function is essentially just a linear regression model, and the activation function does the nonlinear transformation to the input, making it capable to learn and perform more complex tasks. Okay, and if we will differentiate linear function to bring nonlinearity, result will more depend on the input x, and the function will just become constant. It will not introduce any groundbreaking behavior. Of course, if you have something linear and you calculate the derivative, so the derivative of a linear function is just a constant. So you will not be able to learn anything from this. So all the magic here in neural network is from the non-linearity that is introduced through the activation function. Does this make sense to you?
Yes.
Okay. Now, of course, last time when we have calculated the backward propagation, we had to calculate the derivative of the loss with respect to A, and A was the cross entropy, and is based on the sigmoid function. Okay, so here we need to know the derivative of the different activation functions. So in this slide, you can find all of them, or most of them here. For the sigmoid, the derivative of the sigmoid is just the following: is the sigmoid of Z1 minus the sigmoid of Z, and the derivative of the ReLU function is the following: is 0 if Z smaller than 0 and 1 if Z greater than 0. And this is not normal because here you have a constant, so the derivative of a constant is 0, and here we have a linear line, okay, and the derivative of the line is just the constant, which is 1 here because we have x equal to 1. So very simple to find the derivative here. For the leaky ReLU, it will be 0.1 if Z is smaller than 0 and 1 if Z greater or equal to 0. And the tan H is equal to 1 minus tan H of 2. So you can see calculating the derivative of all these functions is simple and straightforward. And basically, it's the derivative is just a function of the function itself. So very simple to calculate.
Doctor,
Yeah.
for relo and leaky relo, if the derivative of them is 0 and 0.1 and 1, so it will not help me to learn, right?
Sorry,
If it's
can
number
yeah, can you
0
repeat
and
the
1.
question?
The derivative of relo and leaky relo is
Yeah.
0 and 1 and 0.1 number.
Yeah.
How this will help to improve weights and bias?
Yeah, this is the derivative of the sigmoid. It's not the derivative of the loss. Okay, the derivative of
Okay.
the activation. It's not the derivative of the loss. Okay, this will be used later on for to calculate the derivative of the loss. But okay, you have confused with the derivative of the loss, but this is not the case.
Sorry, clear now.
Okay, so now let's talk about the gradient descent for neural network. Okay, which is the backward propagation. And in the logistic regression, okay, so we calculated the backward propagation by first calculating the derivative of the loss with respect to A, and then the derivative of the loss with respect to Z, and finally the derivative of the loss with respect to W1, W2, and B. And then when we find these values, we will use them to update the weights by just subtracting like small portion multiplied by alpha, and alpha here is the learning rate. So let's see how we can generalize this for a neural network with a hidden layer and output layer. Okay. So this is the structure of our network here. Okay, I think now the concept of forward propagation is quite easy to understand. We have an input matrix that contains M training examples. Okay, we will feed forward this matrix to the first layer, and the first layer is going to calculate W1 multiplied by X plus B, and then it applies the sigmoid to calculate the output A1, and A1 will be the input of the second layer. So we will multiply W2 by A1 plus B2, we apply the sigmoid function, and finally we calculate an A2 over here. Okay, so this will allow us to calculate the loss, okay, the loss for all the training examples. And for all training examples, we have already introduced the concept of the cost function, which is just the average of all losses. Okay, the average of all losses, the loss between the estimated value of the ith image and the ground truth of the ith image, and then we calculate the average by dividing by m. And this is going to be the loss for the weights for the model. Okay, so W1, B1, W2, and B2 represent our model, because a model, a neural network model, is just the collection of weights and biases of this model. And of course, if the loss of the cost function is greater than 0, we need to optimize with respect to WB, W1, B1, and W2, B2, according to all their weights. Okay, so this is the general algorithm for the gradient descent or for the backward propagation, considering a network similar to this one. So we have our parameters, initial parameters, that will be randomly initialized W1, B1, and W2, B2. We will make forward propagation to calculate the cost function, which is 1 divided by m of the loss, the average loss. And then we calculate the gradient descent. Okay, for every image, we calculate the cost, and then we will calculate the derivative of W2, the derivative of the loss with respect to W2, and the derivative of the loss with respect to B2, with the derivative of the loss with respect to W1, and the derivative of the loss with respect of W2, with respect to B1. And of course, when we find all these four things, we will do the same thing, but here applied at matrix scale. W2 is equal to W2 minus alpha multiplied by dW2, and B2 is equal to B2 minus alpha multiplied by dB2, and we will do the same thing for W1 and B1. Of course, here the equations will be done in the same way, but instead of doing that at the scalar scale, we will do it at the matrix scale. Okay, we need to do the same thing, like calculating the derivative with respect to A2, Z2, and then we'll be able to calculate with respect to W2 and B2. So we need to do it in in the same steps that we have introduced in the previous lecture. Any question here?
Yes, just a simple question. So, in the second layer, we use a sigmoid function, right?
Yes,
Usually.
yes.
And what do we use in the first layer?
No, here it doesn't matter about what you use. I mean, here this is a general equation, okay, about the derivative of the cost with respect to the weight and the bias. And here what matters more is, okay, the expression of the loss at the end. Are you going to use gross entropy, or are you going to use quadratic, and so on?
So
Yes. But of course, the sigmoid function.
So
that
sigmoid
yeah.
is typically used in the output layer.
No, yeah. Sigmoid is used in the output layer. In the hidden layer, you can use sigmoid, you can use ReLU, and you can use tan H. But of course, the derivative is going to depend on what activation function you have in the hidden layer. Okay, because the derivative of the loss with respect to the weight will depend on the derivative of the loss with respect to the activation function. واضح?
Yes, thank you.
Okay. Any other question?
So, Doctor, the way of getting derivative is not explained here, right? But here explained how we use this derivative to improve the weight and bias, right?
Yes. Yeah, because going into all the details, maybe it's much more complicated than the simple case of one neuron. But of course, in the next assignment, you will go into all the details and you will implement all these different derivatives one by one. And you will see that it doesn't differ too much from what you have done in the first assignment. The only thing is that here we have a bigger scale for the matrix representations.
Doctor,
Yes.
so for each layer we use only one method. Yani all the nodes should apply for them the same method. But
Yes.
from the layer to layer we can choose different method or functions.
From layer to layer?
Yes, yani from the output layer we use sigmoid, but the second layer we can use something else.
Yes. هو in general the output layer for classification problems, it uses either sigmoid if you have one output, or it will use the softmax if you have multiple outputs. Okay, and the softmax is kind of generalization of the sigmoid for multiple outputs. In the hidden layer, you can use any non-linear activation function. واضح?
Yes, but in the hidden layer, if we choose a function, we have to apply it to all nodes, right?
Yes. You cannot say, okay, this function is tan H, and so the same layer will use the same activation. And basically the whole network probably use the same activation functions.
Okay.
Yeah. Any other questions?
Doctor, can we have multiple hidden layer?
Yes, of course. This will be the objective of the next lecture. We will calculate the same thing for multiple hidden layers.
And all the hidden layers will use the same function also, or not necessarily?
All the hidden layers, yes, they use the same function.
Okay.
I mean, you can use, nothing prevents you to use different activation function on different layers. But first, I don't remember that I have seen a model that does this. And I'm not sure about whether this is going to be really efficient or even permissible. I don't know. So maybe you can try in TensorFlow to do that. But I'm not sure what will be the consequences. Okay, so now let's go back for the dimensions for one input image. Okay, so for the dimension here, let's say we have, I think we've done this. Yeah, this one, we've done it before. This is kind of a reminder for one input image. The reminder for one input image for a given input X. Okay, now using vectorization, we have 3, 1 here, okay, and we have 4, 3, okay, this is the same thing. This is just the expanded form of the matrix. But here, let's now try to make some generalization. Instead of saying that we have 3 pixels, let's say we have nx pixels to derive a general equation about the different shapes. So here, the vector x will be nx by 1 because we have nx rows. Okay. So what will be the shape of this w here?
W.
Yeah.
mx multiplied with nx.
No. How many outputs we have? We have 4 outputs. We have 4 outputs and nx pixels. So it will be 4
Yes.
by nx.
This is if we assume it's just 4. Okay.
Yeah. 4
Yeah.
by nx. Yes.
Doctor,
Yes.
this 4 is the number of layers, right? In this hidden layer.
The 4 is the number of layers. It's also the number of outputs in that layer.
Okay.
Okay. And here we have 4, 1 because we have 4 nodes in the layer. And this will make the z is 4, 1. Voila. So the same thing, instead of having nx, we have,
But it's
instead of having 3, we have nx now, which is the generalization of the number of pixels.
sorry, but 4 and 1 are not constants, right? So there can be a difference.
Which 4 and 1?
Sorry, I mean just the 4. I mean the 1 is
Yeah, the
usually
four- yeah.
go with 1 column.
Yeah, the 4 depends on the number
But,
of
is
nodes.
the 4 constant?
No, it depends on the number of nodes. If you have 5 nodes, it will become 5, 1. If you have 6 nodes in the layer, it will become 6, 1. Okay, so we can write is n number of nodes in the layer. Okay, so now considering this network with M training examples. Okay, so what we will have for M training examples, first of all, we have nx by m. We have nx by m. So here in this example, we have only nx by 1. So now we will consider the case of M training examples. So this one will become nx by m. Okay, and this will make so the weight matrix will not change. It will be just 4 by nx. Same thing for the bias. Okay, and this, it makes sense. Look, you will multiply this column by this row. This row by this column, and then this row by this column, and this row by this column, until this row by this column here. Okay, and then you go to the second one. So you do the dot product. Yes. So you have 4 nx. Here you have nx by m. So of course here you simplify by nx. You will have 4m. 4m. And this is going to stay for 1, and here you have 4m. It's possible to multiply to add 4m plus 4, 1, so all these values will be added to the vector, and you will find z will be of shape 4m for M training examples. And of course the shape of A will be the same as the shape of z. Okay, so this is w1, x, b1, and z1 here. Okay, so these are the different shapes in case when we process a batch of M training images.
Okay.
Yes.
Doctor?
Yes.
Yeah, when we're adding a 4m with 4.1, it's not possible to add with different dimensions, but does it use broadcasting here to make it possible?
Yeah, this is the concept of broadcasting, of course. I think you have already applied it in the first assignment, right?
It was in the Python basics, yeah.
Yeah.
NumPy, which was not assignment, but it was
Yeah, it uses the concept of broadcasting. Okay, so
it was actually useful during the assignment.
Yes. Yeah, I put you everything that if you do it in chronological order, you will get everything. So yes, this B1 is going to be added to to all the values. Okay, we'll increment all the values of the whole row. So if you take this row, okay, it will add all the values B1. And this is for the second row, for the third row, and for the fourth row using broadcasting. And this will result later on, you will apply the nonlinear function to calculate the output A1. Okay, so the concept of computation is the same. Maybe here you have, as already mentioned, the broadcasting, but every other thing will almost remain the same. Instead of multiplying by just one vector of nx pixels, we will multiply by a matrix that is nx pixels by m training examples. Okay, so let's try to do this for the first training example. Okay, I have hidden all the values of the other training example. So I kept x1, x2, x3, x and x of the first image. And this will allow to find, okay, this column, z11, z211. So z111, what does it mean? It's the z calculated in the first node of the first layer of the first training example.
Image.
Yes, or the first image. Z41 is the z of the fourth node in the first layer of the first image. Okay, and then you can do the same, okay, for the second training example. So here it will calculate the z for the first node for the first layer of the second image, because here we take the second image. Okay, and you do the same for all training examples in the same way. Okay, so let's try to generalize now. For every layer L, it has nx weight. Okay, nx weight for every layer L. So nx is the number of pixels. Not only nx, but nx by the number of output as well. Maybe here for every node, we will have nx weights, and for every layer, we will have nx by the number of output at the end. So this is W, and this is B1.
For W. Now,
Yes.
each row represent what, doctor? For example, one W111.
This one,
Yes.
yeah, we can see this here. Okay, so W111 will be multiplied by X11. Okay, so when you multiply this by this here. Okay, so all these values will be multiplied by all the values by the first pixels of all images.
So, doctor, W11 represent first node for first image and for first pixel, right?
No, this is not related to the image. W11, the W is not related to the image. This is related to the model. And this is why the matrix W doesn't depend on M. Okay? But this value here, look, this value will be multiplied by the first pixel. This value will be multiplied by the second pixel. And this value will be multiplied by the last pixel. Now, when we go to the second training example, this value is going to be multiplied by the first pixel of the second image and will result to this one. So actually Z, we will have a Z for every input image, but W is independent of the images. W is going to be learned from the images.
Okay.
Okay?
Each row represents one node.
Yeah. So here, the index is just below. It represents the index with respect to the pixel. Okay? We have 1 to n x pixels. And the index here, it's on the top. It's related to the training image example. So do not confuse between parentheses on the top and parentheses of the W in the bottom. واضح?
Yes.
Wow.
Yeah, it's a particular notation. I mean, just to wrap up everything together. And of course, now in Python, this can be done using NumPy arrays in a very simple manner. Okay, so now let's look at the forward propagation in the second layer. Okay, in the second layer, we will have the output A1 as input of the second layer, and we will have only one output. So this means, okay, so what do we have here? We have M training examples, and we have
Yes.
four values in the input. So instead of the pixels, we will have the A1 to A4 for the A1 to A4 for every image. Okay, this is why we have here 4 by M. Okay, and here we will have, because we have one input, we have one output value at the end of the layer, so we have 1 here multiplied by 4, because here we have 4 input to that layer. So this is a dot product, 1 4 by 4M. It will result in the value 1M, which will be the size of Z2. And of course, we use broadcasting. We will have here a scalar, and this scalar will be added to all the values that will be resulted from this dot product. And this will be the values of Z2, which is Z1, Z12 for the first image, Z12 for the second image, and Z12 for the nth image. And this will allow to calculate the output of the first image, the output, this should be A2, yeah. Okay, it's A12, okay. This is the output of the second image, and this is the output of the M image. And this makes a lot of sense, because at the end, we will have the output for M images, and we will calculate the loss for M images, and finally the cost function will be just the average loss among the M images. Okay, so this is what we want to achieve at the end, is the cost function, which is the average loss among the M images. So we will calculate the loss with respect to this value A121, and then the loss with respect to the second image A122, and then the loss with respect to the M image A12M, and finally for all the losses we will sum them up together and divide by M to find the average. And if this cost function is greater than 0 in this case, we will apply the backward propagation using gradient descent in order to calculate the increments for the weights. واضح؟
Yes.
Well,
Okay. Okay, now let's try to work out again the shape in a more general way. Let's consider that we have in every layer L, we have NL elements. For example, in layer L1, we have NL1 elements. So in this case, the shape can be the following. So of course, X will be NX by M, because NX is the number of pixels and M the number of training examples. And this W1 will have NL1, the number of nodes in the layer 1, multiplied by NX. So making the dot product, this will result into NL1 by M. Okay, so NL1 by M, this will be, there is something wrong here. Okay, the shape of Z1. I did something wrong here. What is it?
B, Doctor. B is not BNL1.
Yes. Yeah, because B is independent of the number of training examples. Okay, so this is the correct now. And of course, it will use broadcasting here. Okay, and then we calculate A1 by applying now we put a G1 of Z1. G here, it's a nonlinear function. It can be sigmoid, it can be tan H, it can be ReLU. So here I just to make general notation is G1. Okay, G1, it's the activation function that is used in the first layer. It can be sigmoid or ReLU or tan H or any other one. And of course, the shape of A1 will be the same shape as Z1 and L1 by M. Now going to the output layer A2, so we start from A1, which has the same shape here, and L1 by M, and W2 will have 1 because I have only one output multiplied by NL1. So making here the dot product, it will result on 1 by M, which is the size of Z2, and the size of A2 will be here 1 M for M training examples. Okay, the same shape as Z2. And of course, when we calculate the output of M training examples, we will calculate the loss of M training examples here. We will calculate and then we make the average to find the cost function. The cost function will be the assessment for how good the model is and how well it represents the data set. If the cost function is very high, it means that we need to make an iteration of backward propagation by making the gradient descent process, calculating the derivative of the loss with respect to W1, B1, W2, and B2, and finally adjusting again the weight and making another pass of the forward propagation and estimating the cost again. So the process should repeat several times until the cost function becomes as low as possible and close to zero. Okay, so the gradient descent for neural network, for our neural network with one hidden layer is the following. So now I think everyone agrees on the forward propagation expression. So you understand this. So here we can use G of Z1 because we can have any kind of activation function. But here I just write again sigmoid, because in the case of logistic regression, we will use the sigmoid to output one scalar value, which is between 0 and 1. Now for the backward propagation, these are the different equations that you have to calculate. So first of all, we calculate the derivative with respect to Z2, the derivative of the loss with respect to Z2, the output here, which is equal to A2 minus Y. And if, now this assumes that we are using the cross entropy loss, the same loss that we have used in the previous lecture with the logistic regression. Okay, this is why if you look, this is very similar to the expressions that we have derived in the logistic regression lecture, but instead of writing scalar here, we are going to write at the matrix scale. So dz2 will be just equal to a2 minus y, and this will make the derivative of the loss with respect to w2 will be equal 1 divided by m dz2 multiplied by a1 transpose. And also we calculate the derivative of the loss with respect to db2 at the second layer, which is equal in numpy to the following. It is actually the sum of dz2, the sum of dz2, okay, divided by m. So this is kind of the average. And this is the expression that we will be using in the assignment, okay, in order to calculate the sum in the proper way, because the sum in the matrix, we can calculate it with respect to the columns or to the rows. So this is why here we use axes. Okay, so we are going to make the sum of rows values. You will make the sum of the first row, and then the sum of the second row, and then the sum of the third row, and then the sum of the last row. So this is why you put axis equal to 1. If you put axis equal to 0, you will make the sum of the column values. You start to make the sum of the first column, the second column, the third column, and the fourth column. So in this case, we want to do the sum over the row values and divide by m, because we have m training example. Okay, so every row contains m training examples. And this is for just reshaping, keep deems equal to true. We do the same thing to calculate the derivative of the loss with respect to z1. And this is the expression. It's w2 dz2 multiplied by the derivative of the activation function multiplied by z1. And here the derivative of the activation function, it can be the derivative of ReLU, or the derivative of sigmoid, or tan h, or it depends on which activation function you have used into these nodes over here. Okay, so we make it general. And the derivative of the loss with respect to dw1, this is what we want to achieve, is 1 divided by m dz1 xt, and this is the derivative of the loss with respect to the bias b1. It's similar to this expression. So at the end of the backward propagation, we have calculated the derivative of the loss with respect to w2, b2, w1, and b1, and this will allow us to calculate the values of the new weights by making, again, w1 is equal to w1 minus alpha dw1, and b1 will be equal to b1 minus alpha db1, and so on. So we use exactly the same equations that we already introduced in the lecture of logistic regression with one neuron. The only thing that changed here is that the dimensions are different. Okay, so in the case of one training example, you can see that in the case of one training example, you have the derivative is nx1, and if you use the m training example, it will become nl or nl1. This should be nl1 by m.
Doctor,
Yes.
what will happen if we make keep dims false?
You will have computation errors. You can try it in the assignment, okay, and this will make the computation not correct. I explained here in the next lecture, in the next slide, the difference. Now, for example, here, when you make np.sum, this is the matrix A. You will have a matrix similar to this one, and you will make np.sum A, axis equal to 1. So what it will do? It will take this row, so 1 plus 5 plus 7 plus 4. It will find 17. Okay, and here it will find 24, the sum of this row. And here it will find 19, the sum of the last row. So this is if you put keep dims equal to false. This is by default. It will return you a vector with 3 columns. Now you want to make a vector with 3 rows. Okay, so maybe I have to go to this slide. So if you make keep dims equal to 1, it will calculate the same value, 17, 24, 19, but it will keep the same dimension. Look, here you have 3 rows, and here you have 3 rows. However, if you make keep dimension equal to false, here you have 3 rows, and here you have only 1 row. So the dimension here are different from the dimensions here. And when you put keep dim equal to 1, the dimension here, 3 rows, it's the same as the dimension here. So it will create another NumPy array with similar number of rows. It will maintain the number of rows. Now, if you do, for example, np sum axis equal to 0, so in this case, you will make the sum over the column values. 1 plus 5 plus 2 equal to 8. 5 plus 7 plus 7 equal to 19, and so on. واضح المثال؟
واضح جدا.
So I didn't get what happens if we make axis equal to 0, and what's the difference if we make the axis equal to 1?
Yeah, هذا الأكسس equal to 1. Is this slide similar to this one? So axis equal to 1, you will make the sum over the row values. First row, second row, third row. Axis equal to 0, you will calculate it over the column value. Sum of the column, first column, sum of the second column, of the third column, of the fourth column.
I get it.
Okay. And the keep dim here is just if we want to keep dimension, and we want to keep dimension here to be able to make the computation right. واضح?
But did we keep the dimensions?
Yes, here keep dims should be equal to true. Yes, they should be equal to true. In any case, in the assignment, it explains, it will tell you that use keep dims equal to true. But now you understand why. Okay, you can go back to this slide to understand how it works. And this is, for example, axis equal to 0 and keep dims equal to true. Okay, here you will have this, you will maintain the same number of columns because we have made the sum over the columns. Okay, these are the characteristics of NumPy array structure in Python. And this is one of the reasons why Python is used for computing. It is very powerful. The NumPy data structure is really very powerful and provides a lot of functionality and flexibility to perform different types of computations that you don't find easily in other programming languages. Okay. Okay, now we will talk about weight initialization. Okay, so far we have introduced the forward propagation, backward propagation about a neural network with one hidden node, with one hidden layer and one output layer. Now we talk about very important aspect in neural network, which is weight initialization. So this means, so initially when we start a neural network, we don't have any particular value of the weights. So the weights are going to be initialized, and then when we train the model, these weights are going to be adjusted, or these weights are going to be adjusted until it can provide to the lowest cost and to the lowest loss possible. But now the question, how should we initialize the weights when we start a new neural network? And this is the question that we try to respond and investigate in the next couple of slides. Okay, so this is just a summary about the gradient descent for neural networks. So there is nothing new here. And as already mentioned, our objective is to investigate how should we start these W1, B1, W2, and B2 in the beginning of training a neural network model. So of course we have maybe the common way or the intuitive way is to do something like random initialization. So, but let's understand why we need to do a random initialization. Why, for example, we don't start from 0. Let's make all the weights equal to 0. Okay, so choosing all the weights equal to 0 is a bad approach and will not help to your neural network to learn. So let's take an example where, for example, W1 is all equal to zeros initially. So when we do the computation, for example, Z1 is equal to zeros multiplied by X1 plus zeros here. So we will find just 0. Okay, so you can find 0, 0, 0, 0. This is the output of Z1. So nothing to learn here. Everything is the same. And then we calculate A1 by applying the sigmoid of 0 over all these values. We'll find 0.5, 0.5, 0.5, and 0.5. And then calculating Z2 will be just zeros multiplied by 0.5 plus 0, and then it will be 0. And if we may apply the sigmoid, we will just find 0.5. And when we do the backward propagation, okay, so we can apply the different equations that we have seen before. For dz2 equal a2 minus y. This is a2 minus y is equal to 0.5. And we calculate dw2. dw2 is equal to dz2 multiplied by a1. So this is dz2 equals 0.5, and this is the vector a1. We'll find this value. This is db2 and dz1. We just make numerical computation of all the backward propagation equation that we have here in the left side. Okay, you calculate dz1, you will find zeros, and you calculate dw1, you will find at the end zeros. So the problem here is that all the weights at the end will be the same, either 0 or the same, and we will have here a weight matrix that is completely symmetric. So what we have in the first node, it's the same in the second node, it's the same in the third node, it's the same in the fourth node. So all the nodes are going to learn the same thing. So either you have multiple nodes or one node, all the values of W and B will be the same in all the nodes. And this is what we call it symmetric. Okay, so the W and B are symmetric in all the nodes. And this is very bad. Because why we are making so many nodes into one layer? So that for every node to learn something different from the other. And in this case, we will extract different features from the input data. But if, for example, I make 1000 nodes and all of them, they give me the same value, so I have added more complexities without having any gain in the learning process. And this is too bad. This is why it's strictly important to avoid initializing your neural network with zero value. And like the intuitive way is to do a random initialization for the neural network. Does this make sense? Yes.
Yes. So let's say we have 1,000 nodes with the same values. Will the result be the same as if we had, let's say, 10 nodes with the same value because everything's the same? Or will it be?
Yeah. What is the model at the end? Isn't it W and B?
Yes.
So if you have W, if they are all the same, what are you going to learn? Nothing.
Yeah. We did this in the last assignment. We initialized them with zeros.
Yes.
Is this why the accuracy was bad?
Yes, of course. It will lead to bad
Maybe
accuracy.
Doctor, in last assignment, just one node. So it's not a big deal. If it's more than one node.
Yes. And you will see the impact more in the next assignment. Okay, because you have multiple nodes. And for the computation here, I think it's clear that at the end we don't learn anything. All the nodes are going to be exactly the same. Okay, so we don't really learn anything. And this is why we need to make the initialization random. But of course, the randomness here, it has also to be controlled. I'm going to explain you how to do that. Okay, so this is for the weight update. Okay, so we will not have, it will not help to learn anything useful from when we have the initialization all equal to 0. Okay, so in this case, setting all values to 0, setting weights make your model equivalent to a linear model. Okay, so it's something simple, very simple. Even the non-linearity will not have any impact. And when you set all weights to 0, the derivative with respect to the loss function is the same for every W in WL. Okay, and this means that you don't learn anything in the different nodes of a particular layer. All the weights have the same values in the subsequent iterations. And this makes the hidden units completely symmetric. Okay, so putting the weights to 0 is a bad approach and strictly to avoid. On the other side, setting the biases to 0 is safe. So there is no issue with that. And this does not create any trouble if the weights are not initialized to 0. Okay. Okay, so here to summarize, setting weights to 0 is bad and setting biases to 0 is safe and fine. So the random initialization, it means assigning random values to weights, which is much better than setting just 0 assignment. And okay, so in order to introduce randomness, when we say random, it means that we have a probability distribution. They can be, for example, uniformly distributed, or for example, according to particular probability distribution. But here, the common way is that we use the normal distribution or Gaussian. And this is achieved in Python using the rand_n. Rand_n, it means normal distribution. It's a randomness according to the normal distribution, and is used to generate random numbers according to that. So for example here, the right way to initialize W1 is to make np.random.rand_n, and here n1 is the number of nodes in the first layer, and nx is the number of pixels in the first layer. So in our case, we have n1 equal to 4 and nx equal to 3. So it will generate a matrix of 4 by 3, which has completely random values. And b1 is np.zeros, n1 by 1, because here b is going to have 4 outputs. Okay, 4 outputs, so it will be just one vector of size 4 by 1. W2 will be also np.random.rand_n, and we will have n2, n1. So we will have n1 in the input equal to 4, and n2 equal to 1 is the number of output, because we have only one output neuron. And finally, b1 will be np.0 n2 by 1. Okay, we can set it to 0 if we want. Okay, so just equal to 0, because at the end b1 is a scalar value. Okay, so this is an example of initialization using Python code.
Victor, second one should be B2 or B1? Why 2 B1?
Yeah, this one should be B2. Okay, let me change it. Okay, now it looks fine. Okay, so there is another thing to be careful about is should we choose the values are very high or very low, or something in the middle. Okay, let's check the case of a very high initial value. So now we have agreed that making a random initialization is better. Okay, but I can, for example, make a randomness between just 0 and 1, or randomness between 0 and 0.001, or randomness between, for example, 1 and 1000. So there are different ways on how we can set. So imagine that, for example, I can multiply by 1000 these random values, and it will result into random values. But in this case, the values of W1 and W2 will be very high. Okay, so if the weights are initialized with very high values, the term, so the dot product Wx plus B becomes significantly higher. Okay, and an activation function like the sigmoid is applied, so the function maps its value close to 1, where the slope of the gradient changes very slowly and learning takes a lot of time. Now, what does it mean, this work? If, for example, you choose W1 very high, and then you will calculate Wx plus B, okay, so it will be something very high value, and you calculate the sigmoid. Let's say, for example, wx plus b is equal to 10. You calculate the sigmoid of 10, and it will be located here. So the sigmoid of 10 is almost 1, and the derivative here is almost constant. Okay, maybe it's not constant, but it's very, very, very small. It's very close to 0. What does it mean the derivative is very close to 0? It means that the next weight that you are going to calculate will be pretty much similar to your initial weight. And what you will do? You will do W1 is equal to W1 minus alpha, the derivative, صح ولا?
Yes.
And if the derivative is close to 0, so it's almost you make W1 is equal to W1. You will not make substantial change of the weights after you make the derivative of the loss. Okay?
Yes, so it will change slowly.
It will change slowly, yeah. So making the random value as very high is not a proper way as well. Although the values are random, but we need also to control the randomness, the scale, the range of the values that we change, that we choose. On the other hand, let's imagine that we choose very small values. Like for example, W1 is equal to a random number multiplied by 0.00001. Okay? This is also another problem. Because if the weight are initialized with very low values, it gets mapped to 0, almost to 0. Almost the weight is equal to 0. Where in this case, it will be very close to the above. Okay, when the weights are equal to 0, so making the change every time, so you will have W1 is equal to W1 minus alpha dW1. So it's like you have 0 is equal to 0 minus, and you will have a very small change in every iteration. And you will end up at the end, but by all your weights will be going very close to 0. And this problem is referred to as the vanishing gradient. Okay, the vanishing gradient, it means that the value of the gradient is going to vanish from one iteration to another until it becomes 0, and you will end up by not learning something substantial. Okay, so to summarize, like choosing very high values and very small values is not a good approach for the random initialization, and the proper way is to use something in the middle. Assigning reasonable small initial values will lead to a better training performance. Okay, so we want the slope to be something around these points over here. Okay. Okay, so these are just a few more details about the weight initialization. You can read about them when we choose two small values and two large values. Okay, it makes here a simple numerical example that make the calculations. But it's basically is going to lead to the same observation that I have introduced over there. Okay. So how to find appropriate initialization values? To prevent the gradient of the network activation from vanishing or exploding, we will stick to the following rule of thumbs. Okay, so there are two different rules that we try to follow in order to make a good random initialization. First of all, the average of the activations should be 0. And the variance of the activations should stay the same across every layer. So this means that we will try to make some initial values of the weight and W such that if I calculate the activations, okay, they will be close to 0, the activation values. And the variance should be the same across all the layers. And okay, here I'm not going into the math detail. You can check this. And this is called the Xavier initialization. Okay, the Xavier initialization, it will impose these two rule of thumbs. The mean of the activation should be 0, and the variance of activation should stay across every layer. Okay, let's look at this demo here from deeplearning.ai. Okay, I really recommend you to go through all this page because it provides a very good explanation and also some concrete and animations about what happens when you choose when you choose very simple, very small or very large initial values. So for example, if you put 0 here, we have here a neural network with two input values, x1 and x2, and here we have different, this is first hidden layer and the second hidden layer, and we want to train the neural network to classify these points over here. Okay, you can even choose which activation function you want. Select whether to visualize the weights or gradient of the network. So let's start by the weight here and put here. Look at the cost. When you make 0 initialization, the cost doesn't decrease. So what does it mean? It means that the network is not learning anything.
No learning.
Yes. Okay, let's now try to make appropriate initialization value. Okay, look at the cost.
Decreasing.
Yes, and look here, the resulting classification. Okay, so the blue region and the red region are well classified here.
There are two different classes.
Yes, and the cost keep reducing over time. These are to visualize the gradient, and this is to visualize the weight. It shows the scale of the weight here. Now, for example, let's try to replay this by using two small values. So okay, so what happens here?
Anything.
Okay, maybe it's a little better than 0, but still it's like you are doing 0. Look, it starts to decrease, but it's very, very, very slow.
Take a long time.
Yeah, it took a long time in order to start decreasing. Okay, so you have seen that it spent much more time, okay, trying to optimize until it reached some good values to start actually learning something. And now, for example, if we try too large, so we got also another issue. The cost still remained very high, although we tried to make some subdivision, but it's not perfect.
Even worse than too small.
Yes, yes. So I don't know whether we have to wait much longer, but it doesn't seem to provide any improvement. So here, this is just to illustrate that the weight initialization has a big impact on the training of neural network. Now, basically, for the weight initialization, the most used technique is based on Xavier initialization, and it's based on the assumptions that I have introduced over here. Okay, which is the mean of the activation should be 0, and the variance of the activation should stay across every layer. In the assignment, you will have to implement these activations to satisfy this requirement. And when we work with TensorFlow, just if you choose the Xavier initialization, it will provide you this property. Okay, so we come to the end of the lecture, the theoretical lecture for today. I don't know if you have any question about that.
Yeah, doctor, about the bias when we initialize it to 0. Will it still be the same for every instance, the bias?
The bias equal to 0.
If it's, or will it change?
Yeah, the bias equal to 0, it does not affect. Okay, what really affects the learning is the weight. So the bias, you can see it as kind of a corrective constant. But what really matters for the feature learning is actually the value of the weight.
And
because
can we make random like the weights?
Yeah, you can make random. It will not affect. It will not affect, yes. Whether you put them random or set them to 0, it will not affect the performance. Because the weights have more weights actually in the learning process as compared to the bias.
So the bias stack doesn't affect that much?
No. Yeah. Any other question?
Yes, Doctor, I have a question.
Yes.
Doctor, if you can open the fourth slide, please.
Fourth.
Yes, the fourth one.
Yeah, this one.
Yes, here in the yes, in the example of the x1 and x2 and x3. Now in the a1 and a2, the difference between of them, the w and b, because it's taken the same input layer, right?
Yeah, we have explained this actually when we talked about the shape. Let me go to the slide where we talk about the shape of these matrices. Because without the shape, it's difficult to understand what's going inside. I don't remember where. I think it's here, yes. Yeah, this slide. So what is your question now? These are the same
It's
equation.
the difference between yeah, I mean the difference between every new year, that's A1, A2, or A1, is the W and B, right?
Yes, W and B. So W and B are the model of every layer. Okay? So
Okay,
these values will be learned during the forward propagation and the backward propagation. So every time you calculate the loss, and then you will make the derivative of the loss with respect to W1, B1, W2, and B2. Okay? And based on this, you are going to tune these values until the cost becomes as much small as possible. واضح؟
Yes, Dr. واضح, thank you.
اوكي. في سؤال آخر؟ Okay. Okay, fine. Inshallah, we will, after Salat, inshallah, we will do the cut not cut classifier again for the evaluation notebook. So we will do that, and then we will start how to build the data set. Okay, so that's fine for now. Let's come back at 6 p.m. after Salat.